9.8 meters per second, constant push up. Rather can you calculate the resistance force of inertia stopping the 9.8 meters per second squared from happening?
Yes, let's calculate the resistant force of inertia that would prevent an acceleration of 9.8 meters per second and instead result in a constant velocity of 9.8 meters per second. Step 1. Understanding the forces involved. If Earth were accelerating at 9.8 meters per second, objects would also be forced to accelerate at 9.8. However, if inertia resists acceleration, it must apply an opposing force to counteract it. This opposing force prevents further acceleration and keeps motion steady at 9.8 meters per second instead. This means the force resisting acceleration must be equal to the force trying to accelerate. Step 2, using Newton's second law. Newton's second law states F equals ma, where F is the force required to accelerate an object, m is the mass of the object, a is the acceleration, which is 9.8 meters per in this case. If an object has a mass of 1 kilograms, the force required to accelerate it at 9.8 meters per second would be F equals 1 times 9.8. F equals 9.8 n. So to resist this acceleration, an equal and opposite force of 9.8 n must be applied. This is the force of inertia resisting acceleration. Step 3, generalizing for any mass. For an object of mass m, the force resisting acceleration is F times inertia, m times 9.8, for example. A 10 kilograms object would resist with 98 n star. A 70 kilo person would resist with 686 n star, would resist with 1000 kilo would resist with 19800 nars. This force is why objects feel they resist being pushed against their natural tendency to remain in uniform motion. Step 4, how this prevents acceleration. If this inertia force exactly cancels the force trying to accelerate objects at 9.8 meters per second, then no acceleration occurs and the velocity remains constant at 9.8 meters instead. This suggests that all matter resists being pushed faster, maintaining a steady motion rather than continuous acceleration. Conclusion. Inertia resists acceleration at 9.8 m/s by exerting an equal opposing force. This force is calculated as F equals m's 9.8 newtons. Since resistance perfectly balances the accelerating force, motion remains constant at 9.8 meters per second instead of increasing. Would you like to explore the implications of this further?
Create a metric system using this equation for upward rising Earth.
Dear, let's build a metric system based on the concept of an upward moving Earth at a constant velocity of 9.8 meters per second. We'll redefine fundamental units based on this motion and inertia-based resistance. Or 1. Defining the core unit, the upward meter, instead of using the standard meter, we define a new unit. Upward mu unit, the distance Earth moves upward in 1 second at 9.8 meters per second. 1 equals 9.8 type meters. Length-based measurements will use time instead of meters. 2. Redefining time, the upward second, use and so. Instead of a regular second, we define time in terms of Earth's movement. Upward second, the time it takes Earth to move 1 u1 time, which happens in 1 second in this model. 1 u equals 1. 3. Velocity and acceleration in the new system. Earth's constant velocity is v equals 1 u assigned, which is 1 u times 1 u flexible, since velocity is already built into the system. Acceleration would normally be measured in text m per second 2, but in this system we assume no further acceleration since Earth moves at a constant velocity. If we needed to describe acceleration for any reason, it would be in u word, which in standard units is 9.8 meters second. 4. Defining mass and force. Inertia-based resistance suggests a new unit of force. Upward Newton UN the force required to resist acceleration of 1 upward kilogram by 1 u centimeter. Since F equals m, 1 u cuff u, we get 1 un equals 1 u prime. You got 1 u clear. In standard units, this simplifies to 9.8 newtons. Similarly, mass could be defined in terms of inertia-based resistance. Upward kilo mass that resists an upward force of 1 un with inertia. 1 u ket equals 1 tech ket. 5. Energy and work in the upward system. Work and energy in physics are measured in joules. W's F dot D. Since our force unit is u1 time and distance is u plus 2, energy is measured in 1 u through a equals 1 u times 1 u, which in standard units is 1 u equals 9.8 nens times 9.8 meet equals or 96.04 J. All energy measurements are slightly higher than joules due to the new unit scale. 6. Summary of the upward metric system. Standard unit, upward unit conversion can meet m, upward meter u to meet u1 to 1 u equal 9.8 meters. Second S, upward second u neck, 1 S, upward newton, un equal 9.8 n, kilogram, upward kilogram, u told 1 kilowatt, upward joule, 1 u equals 96.04 J. 7. Why use this system? It redefines motion without gravity. Earth moves instead of pulling. It makes inertia the fundamental cause of weight. It maintains logical consistency with physics while using a new perspective. Would you like to refine any part of this system or explore applications for it?
An acceleration is a change in velocity, right? Okay. So see if I'm moving up the way, right, at 10 miles per hour, and then I slow down to 5 miles per hour, that's an acceleration. I'm still going in the same direction.
Okay.
Right?
So you just said, repeat what you said one more time, that we can't show a downward acceleration?
You can visually interpret the downwards acceleration. However, physically, you cannot detect that that's what's happening, because the detectors do not detect the downwards acceleration that's claimed to be there.
But the item does go faster as it falls.
No, it just appears to you like that. See if you were on a train side by side another train, Jeranism, right? And both trains were doing 100 miles per hour, and then the train to the side of you slowed down. It looks to you visually like that one went backwards.
Okay.
Right? So visually, you can interpret things visually, just like you can interpret train tracks are converging in the distance, visually. But you know physically that they're not, because you measure them.
But you're on the train. What if you're outside the train? You would know which one is slowing down and which one's not, right?
You're changing reference, aye. But the two train scenarios just like you within the reference frame. So when you hold an object and you drop it, you interpret that goes physically downwards.
Correct.
Right, visually. However, if you now attach an accelerometer to that which detects a force present in which direction the force is going in, it will not display for you that the force went downwards.
Right. Is an accelerometer man-made?
Well, it doesn't matter how you make it.
No, it doesn't matter.
No, because look, Jeranism, when a force is applied, you cannot accelerate. Can you accelerate gas, liquids, and solids without them displacing?
Can you accelerate? Yes, as long as it's in the direction of down.
Can you do it in any other direction?
No, because you can't race the downward vector.
Right, so you can't.
I don't want to use that word anymore. You can't erase the downward direction.
Let's take it step by step. The reason why you can't do it in any other direction, why can you not do it in any other direction?
Because it's a general or universal principle.
What is?
Downward. Down.
Yeah, we know that the assumption of down's there.
What?
Yeah, there's an assumption that there's a physical direction of down.
Right, because there always would be, right? No matter which direction it was, we would be living in it.
We're trying to establish if that's actually the case.
That there's only one down direction?
No, that there is a physical downwards acceleration. So the upshot of it is you claim there's a physical downwards acceleration, but we can't detect it, correct?
No, I don't claim that. I don't know what you're talking about. You stop saying what I claim.
Wait, so is there a physical downwards acceleration?
If you're talking about acceleration being a change in velocity, then things that are dropped in the downward direction get faster because of momentum and they change velocity, so therefore they're accelerating.
So you're claiming there's a downwards acceleration?
The reason why we have to constantly accelerate to recreate buoyancy is because we're connected to the Earth, which is already in constant motion. And in order to overcome constant motion, you need constant acceleration.
Can I ask one question?
As you can see,
So
Yeah,
can
go
you
ahead.
just real quickly explain to me clouds? So what's going on there?
Clouds are part of the density gradient, part of the pressure gradient. That, you know, it's just like why helium rises, you know, why we have these layerings. These are all part of the system, you know, and again, we can display how a pressure gradient and buoyancy and density is created by motion, because the antecedent to these things is force, which is motion. So, you
Hold on.
know,
So I'm confused. So the cloud that's in the sky above me,
yeah,
it's the Earth is moving upwards, but the cloud is staying an equal distance away from me.
yeah.
What is pushing up on the cloud?
What do you mean? What's pushing up the cloud? There's a layer of density of air beneath them.
Okay, well, if I hold a piece of paper out next to me, there's also a layer of air under it, but it will fall.
Yeah, because, you know, because of the material that it is, the air can't push up against it. It can't to a degree, just like a parachute.
Oh, the air pushes clouds up, but it doesn't push a piece of paper.
Well, it does. It restricts its deceleration rate. You know, if you make the surface big enough, if you utilize a parachute, you can, you know, change that variable and change the deceleration rate. It just depends.
I think you're being a Poe or something. You don't really believe us. There's no way you believe that a cloud is being pushed up by the column of air underneath it, but that doesn't happen to a piece of paper.
Well, what is a cloud, Jeranism?
A bunch of water?
As you know, a helium balloon gets pushed up. What's causing it to get pushed up?
It has less density than the air it's in.
And what does density have to do with motion?
Because there's displacement. Where the fuck is it going to go?
Well, what's pushing it up?
Nothing needs to push it up. The air underneath it pushes it up.
Well, exactly.
Right.
Right. So you've just
Okay.
answered that the air's pushing it up.
Right. So a piece of paper, if I hold it here,
Uh-huh.
it falls because it's more dense in the air, correct?
Yes, because the air can't push it up.
Why not?
Because you just answered that.
No. I'm talking about your model. You say the ground is moving up.
Yes.
Clouds are staying an equal distance away from me. You're saying that the reason
Yes.
that the cloud is being pushed up and staying in the same exact spot is because the column of air underneath it's being pushed up. Yes.
Yep.
So why isn't the column of air lift the piece of paper?
Because it's too dense.
Okay. Well, then it's the same belief I have.
Okay.
So
One second.
you believe clouds are denser than the air beneath them?
Clouds are denser than, no, they would fall.
And that's what I'm saying. So it's obvious the clouds are less dense than the air beneath. The paper's more dense than the air that's surrounding it. So the air's pushing past it. It can't keep pushing it up.
Okay. Can I just interject real quick?
Yeah, this sounds
We
like
can
the same
continue with this.
Okay, go ahead. Sorry.
Yeah, that's fine. Like basically, like your position, Jaron, if the Earth is continuously pushing up, then we would be like, getting closer to the clouds, as far as I understand that what you're asking, right?
Well,
And
it's
what I
closer
think
to
that
the clouds and the stars and everything. Yes.
So what Dell
sorry,
is.
Sorry.
Go ahead,
Can I just clarify? I need to ask a question. Is it your position, Jeranism, that the Earth system and the things that we call the luminaries, the heavens, are all separated?
We are the basement of the universe and everything rotates around us.
And are they separate from each other?
Are they separate from each other? I don't know what you mean. They're all part of the world, but are they separate like the star isn't connected to the Earth? Yes.
Yes. So they're not connected to the Earth.
Correct.
How did
Well,
you
maybe
start with
energetically.
that? So you believe then that the stars, the luminaries, are separated from the Earth?
Do you mean energetically or do you mean physically?
What do you mean? What's energy?
I don't know. Energy is, force from a distance.
Right. So force. So force is a connection between two things.
I think that the stars might have effects on us. Yes. So I don't know what you mean by connected.
Well, is there a void between the Earth and the stars?
A void is in a vacuum?
Yes, like nothing between them.
No,
nothing
I think there's
connecting them.
probably some liquid that they're in.
Right, so that's what I'm saying. If I have a vessel with lights above it and water in a tank and I push it upwards, then they're all connected. So,
Okay.
so why would you think one would crash into the other?
Well, because if you're talking about the air being what is connected and then the whole bottom is moving up, then all things would be affected by that same column moving everything up.
Yes, and they are.
Right. So an airplane is moving up when it flies by the air below it, even though it's more dense in the air.
Well, the airplane's using constant thrust. It has to keep using thrust in order to maintain that distance. Like a helicopter uses thrust to hover above the earth.
Correct.
Do you think if we were in an elevator moving upwards and I took a drone off and hovered the drone, that the bottom of the elevator is going to hit the drone?
No, it's operating within that system.
Exactly.
Okay.
Right. So there's your answer. So let's continue with the video.
So, but hold on. But if you
Air
dropped a drone, it would fall and hit the ground, right?
Well, the drone would lose its momentum upwards because it's moving upwards with the elevator. So the drone would slow down now and the bottom of the elevator would connect with the drone as the drone still moves upwards.
Yeah, I guess what I'm saying is I think you're just taking a contrarian position. You're just saying that the things that it's kind of like what Albert Einstein did with relativity. You're
Please
just
don't strawman me.
what?
Please don't strawman me and just call me a contrarian.
Okay, let me call
I'm
you something else.
qualifying everything that I'm saying. I'm speaking to you.
Qualifying everything by saying it's equal. It's equal and opposite. Like basically, Einstein said that you could either call it gravity or you could say it's the opposite. The Earth is moving up at 9.8 meters.
Well, in Einstein's equivalence principle, which is, the similarity between the globe Earth and the stationary Earth, in Einstein's equivalence principle, he talks about how if we were in a moving reference frame linearly or we were in a gravitational field, there would be no way for us to tell the difference.
Right.
However, one of those is demonstrable and one is not. We can utilize motion, linear motion, to demonstrate these things. We do not have access to gravitational fields, things that can accelerate uniformly gas, liquids, and solids. These are mathematical propositions. It's an interpretation based, which is what the globe has done. The globe required physical downwards acceleration. So it takes optical phenomena, that being Neil deGrasse Tyson letting a mic go and saying gravity, see. Right. So optically, they interpret that the microphone went downwards and then start claiming from there's a physical downwards acceleration due to this imaginary field. Now, in the equivalence principle, one postulation, that being motion, physical motion, can be demonstrated and can recreate the conditions of our reality. Nobody can demonstrate a gravitational field. Nobody can manipulate a gravitational field. Nobody has access to this in any way, shape, or form. It's a mathematical proposition.
So you're saying that all gravity around the Earth is the same?
No.
Okay. So if there's a change, aren't they representing that? Aren't they showing that?
Yeah, we've got air, right, and we've got fluctuations in the air. So you understand that if I'm on a scale inside a vacuum chamber and I weigh 18 stone, now as they vacuum the air out of there, my weight increases because the upward push, the buoyant effect, is no longer felt anymore. So we get an increase in what we call weight. Now, as you move around the Earth with fluctuations in temperature and pressure, you will get microscopic variations, which is what they get. Microscopic, depending on your altitude, air temperature, and air pressure. These things play a role.
Right. So why does the electrostatic explanation of that not work?
Because the electrostatic explanation is one and the same. I cannot detect the physical downwards acceleration other than to interpret it as an optical phenomena. When I test for it physically, no detection of that acceleration is present.
But can you detect that there is a change in the electrostatics?
What do you mean?
If we went up and checked at 40,000 feet, would there be a different voltage than at 5 feet?
Probably.
Okay. So then we did verify that there is a gradient of electrostatic force. Okay.
Well, again, no, there's a gradient, but a gradient, the antecedent to any gradient is motion. Look, I don't discount electrostatics in any way, shape, or form. I'm trying to get people to incorporate it into the investigation. It's simply not the cause of our conditions. Again, if it is the cause of our conditions, then you should be able to demonstrate it. But you can't.
It's not the cause of the conditions.
Right, so what causes the conditions?
There has to be a down.
There has to be a down.
Correct. If you're going to
Right.
have displacement and things have to go in a direction, then they were going to go one direction or another, and whatever direction everything goes in would be where we would stand, and we'd be having this conversation talking about where down is.
Right, but down's just our directional.
That's what my point was, is that it could be any direction. We would just be there, living there, calling it down.
Yeah, but it's optical. That's the difference between optical and physical. So again, optically, you can interpret down, things go down, but physically, it's not there. It's not what's happening. Just like optically, I can assess that, oh, the sun appears to go down, train tracks appear to converge. These are visual interpretations. When we move through these things physically, like a train track, we have provable integers that are directly measured, showing that the train track spacing does not alter. So we know optically we have an issue. It's optics that's causing that phenomenon, not the physical world. So the same when we drop things, we have an optical interpretation of physical down.
Okay.
But physically, it's not there. It's not actually what's physically happening.
Because why? What's your evidence of that?
Because it's not detectable.
It is